So, good afternoon to everybody. So, today let us discuss on energy interactions with the Earth surface features. So far we have discussed about the fundamental concepts of remote sensing, wherein the data is being recorded without any physical contact with the object. That means by making use of various sensors which are present in the aircraft or spacecraft, we are remotely collecting the data. So in case of remote sensing, we have data acquisition and data analysis. The data acquisition involves the sources of energy, then it has to propagate through the atmosphere, and when it propagates through the atmosphere, see, sun is the chief source for the electromagnetic radiation, and when the energy propagates through the atmosphere, there is a mechanism called scattering and absorption. Scattering is nothing but dispersion or diffusion of radiation by the atmospheric particles. Depending upon the interacting electromagnetic radiation and the atmospheric particle size, we have Rayleigh scattering, Mie scattering, and non-selective scattering. So normally, due to this scattering, the contrast of the image get reduces. In addition to the scattering, there is a absorption. There is a absorption. Atmosphere is made up of gaseous molecules, dust particles, and all. Atmosphere does not allow all the electromagnetic radiation to pass through it. Only certain wavelength of the electromagnetic radiation can pass through the atmosphere. So the atmosphere, which is acting as a transparent media, or where the absorption is minimum, that is considered as the atmospheric windows. So we have the atmospheric windows in the visible region, in the infrared region, mid-infrared region, thermal infrared region, as well as in the microwave region of the electromagnetic spectrum. And finally, these wavelengths will be reaching the Earth's surface, whereas gamma rays, X-rays, UV rays and all are absorbed by the atmosphere. So they are not at all reaching the Earth's surface. So when we talk about terrestrial remote sensing, the role of these wavelengths are negligible. So they are not playing any role. Now let us discuss how the energy interacts with the Earth surface features. So when the energy interacts with the Earth surface features, so let us discuss these things in detail. So see, this is the basic principles of remote sensing. Remote sensing, and all of you are familiar about the electromagnetic spectrum. And now let us see how energy interacts with the Earth surface feature. See, this is the incident energy. When the incident energy reaches the Earth surface, part of it will be reflected back, part is absorbed, and part is transmitted through the object. And this can be expressed by a mathematical equation, that is EI lambda means ER lambda plus EA lambda plus ET lambda. That means reflection, absorption, and transmittance will be there. So the basic principle here in remote sensing is all the three, that is reflection, absorption, and transmittance, will be different for different surface features. And based on that, we will be able to differentiate the Earth surface features. And we must remember one more thing when we are considering this equation. Just now I said these three will be different for different Earth surface features. So for example, the sandy beach or the desert sand or the dried up sand, which reflects maximum light, whereas the water bodies, which absorbs most of the electromagnetic radiation, in between you have different shades of gray that are nothing but they are representing the reflectance of the Earth surface features. If it is a very bright surface feature, it will have maximum reflectance. Then if it is a dark object, it absorbs most of the electromagnetic radiation. So when we talk about this, see here we have the digital numbers. So normally the satellite data are represented in the digital number. So if it is a 8-bit data, the data will be having a value from 0 to 255. 0 is the darkest object and 255 is the brightest object. That means there the reflectance will be very high. These pixels are showing the highest reflectance, and that are represented here by number 255, whereas these are having the lowest reflectance. So that means here the absorption will be more. They are having the lower digital number. That is how we have to differentiate the surface features on a remotely sensed data. Then coming to this, see, just now I said there will be a reflection, absorption, and transmittance when the energy falls on the Earth surface. So it will be different for different Earth surface features. Now let us discuss what is spectral reflectance. Spectral reflectance is the fraction of incident radiation that is reflected by a surface. Now the reflectance characteristics of Earth surface features, we can quantify it. How to quantify? Which can be quantified by measuring the portion of the incident energy that is reflected. This is measured as a function of wavelength and is called as spectral reflectance. Now, when we talk about the spectral reflectance curves, see, we are getting the spectral reflectance values in percentages. And if we plot the spectral reflectance versus wavelength, we are getting the spectral reflectance curves. See, the necessity, why we have to plot the spectral reflectance curves. Here we have the spectral reflectance curves for vegetation, soil and water. These are the important basic cover types. See the green curve. See here, there is a peak in the green region of the spectrum. There is a dip in the blue and red region of the spectrum because vegetation reflects maximum light in the green region of the electromagnetic spectrum. That is from zero point 0.5 to zero point 0.6 micrometer or 500 to 600 nanometer range of the spectrum. Then immediately next to the red, we have the near infrared region of the spectrum. There you can see vegetation reflects about 50% of the light. In the visible, again in the green region, it reflects about 10 to 15% of the light, whereas in the near infrared region of the spectrum, vegetation reflects about 50% of the light. So that is why normally vegetation is represented by bright red color or red color on a color composite. Wherever bright red are there, they are very healthy vegetation, and difference in red will tell us the status of vegetation. So normally on a color composite, we will be able to identify the vegetation based on the color, especially red color, because vegetation shows maximum reflectance in the near infrared region of the electromagnetic spectrum. That is why on a false color composite, vegetation is represented by red color. Then here you have two dips at 1.4 and 1.9 micrometer range. That is mainly because of the water molecules. Water molecules present in the leaves, they absorb the electromagnetic radiation. That is why you are getting dip. But see again, if you see the soil, it is showing the increasing trend from the visible to the near infrared. But again, there are two dips at 1.4 and 1.9, and one more is there at 2.2. This is again because of the moisture content in the leaves. They absorb the electromagnetic radiation. That is why there is a dip. Then if you consider the water body, see, there is a reflectance in the visible region of the spectrum, but from zero point 0.7 onwards, zero point 0.7 micrometer onwards, vegetation absorbs all the electromagnetic radiation. That means it looks black. Why it looks black? Because it absorbs all the electromagnetic radiation. There is no reflectance at all. See, now by plotting these spectral reflectance curves, we are getting some idea about the spectral characteristics of the Earth surface features. Just now I said we have the basic cover types like vegetation, soil, and water. By plotting this, we will get some idea, and based on that, we can select which are the best wavelengths or bands for a particular application. When I go for vegetation mapping, definitely I will prefer this near infrared bands because it shows maximum reflectance. Vegetation shows maximum reflectance in the near infrared region of the spectrum. In a similar way, water bodies absorbs the electromagnetic radiation in the near infrared region. So wherever water bodies are there, that can be demarcated based on the absorptional feature. So wherever deep waters or water spread areas are there, that can be demarcated based on the spectral reflectance values. So this is again one more curve. So one more slide showing the spectral reflectance of various cover types. See here, there is a peak in the visible region of the spectrum for vegetation. That is mainly because of the presence of chlorophyll. When the chlorophyll production gets reduces, so the vegetation turns to yellowish. So that is combination of green plus red. So whereas here, if you see, vegetation reflects maximum light in the near infrared region of the spectrum. That is mainly because of the cell structure. Because of the cell structure, there will be highest reflectance in the near infrared region of the spectrum. And again, because of the water molecules present in the leaves, there are two depressions at 1.4 and 1.9 micrometer respectively. Then we have the clear water, and turbid water will have always higher reflectance than the clear water. But from 0.7 onwards, there is no reflection at all for water bodies because they absorb most of the electromagnetic radiation. Now, if we divide this in what is spectral reflectance, I said spectral reflectance is nothing but how much of energy reflected back from the Earth's surface. So here we are getting the spectral reflectance values in percentages. See here, for example, we have the true color imagery and false color imagery. In the true color imagery, that means vegetation is represented by green color, that is combination of blue, green plus red. And here barren land, then some other type of vegetation, then cropland and all are present. Even you can see the coconut vegetation that is showing green color and all. Of course, this is the true color imagery. This is from the Google image. And one more true color imagery where the vegetation is represented by green color. So wherever green color is there, definitely you can say all of these are vegetational features. Then different surface features will show different colors even in the true color imagery. Now coming to the false color composite, I said vegetation reflects maximum light in the near infrared region of the spectrum. Of course, this is the Indian remote sensing satellite imagery, list 2 imagery of the coastal Karnataka, Mangalore coast you can see. This is Netravati river, this is Gurupur river and Mangalore port is here. Even you can see the breakwaters near the port as well as near the estuary. And you see here the water bodies, see, they look almost dark, whereas the sandy area, they show bright reflectance. So in a similar way, vegetated areas are showing bright red color. So difference in red will help me to differentiate the type of vegetation, what type of vegetation is present, where we have the healthiest vegetation, where we have the diseased vegetation and all. That can be differentiated by using the color composite. It is not the true color of the terrain. That is why it is called as the false color composite. Even you can see the river course here, Gurupur river, it is dried up. That is why on the river channel, you cannot see any water bodies, whereas here the river is flowing almost throughout the year. That is why you have the water bodies in the Netravati river you can see. Of course, this is one more satellite imagery of northern part of Udupi district. You can see the Western Ghats and geological faults and all. You can see here water bodies, then turbidity levels in the near shore areas and all. And here this is the coastal plain. So different surface features can be identified, and by plotting the spectral reflectance curve, see for example, when I am ordering for the satellite data products for the interpretation purpose, I must have the knowledge what type of data products must be used for a particular type of application, which are the wavelengths, which are the wave bands normally should be used. For that purpose, I must have the knowledge. That information I am getting by plotting the spectral reflectance curves. Now there is one more formula is there to identify the healthy vegetation and diseased vegetation, that is called as normalized differential vegetation index. It is popularly called as NDVI. Here we have to take the reflectance values in the near infrared region as well as in the visible red region of the spectrum. See, the formula is NIR minus visible red divided by NIR plus visible red. That means here we are considering the reflectance in the near infrared as well as in the red region of the spectrum. Of course, red absorbs all the electromagnetic radiation, whereas in the near infrared vegetation reflects maximum light. So here for the healthy vegetation, the NDVI values are higher. That means if you get higher NDVI, that means it is the healthiest vegetation. And if you get lower values, sometimes it goes to negative. That means it is the diseased vegetation. If you get, see, normally not NDVI values ranging from -1 to +1. So here, again, I said, see, we are making use of this multispectral remote sensing concept in remote sensing to differentiate the Earth surface features. See, for example, we have two types of vegetation. One is deciduous forest, the other one is coniferous forest, the narrow-lived species, and deciduous trees are broad-lived species. Now, there is a need to demarcate these. For example, maybe along the Western Ghats, we have the deciduous forest, we have the coniferous forest and all, and how best we can make use of this multispectral data to differentiate these two types of vegetation. See, I'm getting the multispectral data through satellite remote sensing. See, if I go for the blue region of the spectrum, see, for example, here we have the multispectral scanner of Landsat data. zero point 0.4 to zero point 0.5 is the blue region of the spectrum, and 0.5 to zero point 0.6 micrometer is the green, 0.6 to zero point 0.7 is the red region, 0.7 onwards, up to 0.9 it is the near infrared. if you observe here carefully, in the blue, green, and red, this vegetation will have almost similar reflectance and absorption. Blue and red are absorption bands, and green is the reflected band. See, but the difference is not that much to differentiate two types of vegetation. But when I go for near infrared band interpretation, see, coniferous trees are having lesser reflectance, that is about 25 to 30% of the light get reflect from the coniferous, whereas deciduous trees shows higher reflectance. So broad-leaved species will have higher reflectance than the narrow-leaved species, coniferous trees. So that is how I can differentiate the vegetational features based on where if I have the deciduous trees, where I have the coniferous trees and all. So I will succeed in differentiating these two types of vegetation when I go for multispectral data analysis. In the sense, in the beginning, we have discussed when the energy interacts with the Earth surface features, part of the light will be reflected, part is absorbed, and part is transmitted. These three will be different for different Earth surface features. That is point number one. Point number two is again reflection, absorption, and transmittance will be different at a different wavelength of the electromagnetic spectrum that is clearly visible on this image. So thank you for your patience hearing. Thank you.